record? It's working. Great. All right. I will use a document camera. And so now I hope that everybody can see this equally well. You're recording already. That's great. That's all going to be part of the welcome on YouTube. If you're watching this on YouTube, great that you're here. I'm going to start with my talk on high-dimensional cohomology, moduli spaces, introduction to this masterclass. So first things first, what's a moduli space? And a moduli space in general is maybe a space that it could be a topological space, a variety that will classify certain things. It could classify objects like curves. It can classify bundles, and in particular, it will be a classifying space for a group as well in all of our cases. So moduli spaces classify objects, bundles, and maybe as an example, first example is the Grassmannian. G are, let's say, K in Rn is the set, as a set, it's the k-dimensional subspaces of Rn. And you can give this space a topology and even an algebraic structure. For example, what you could do is you start with that you take k tuples of Rn vectors, and then you take a this is a topological space, and you take a subspace of this, which is called the Stiefel manifold, which is the tuples of k Rn vectors that are linear independent. Maybe you want that they are being orthonormal basis or something that is similar, works similarly. And then now you can act with the general linear group with of k times k matrices on these vectors and mod out by this. Or in other words, you can just think of the quotient. Everything every tuple is the same if they span the same vector space. And so in that way, GRK Rn is the same as the Stiefel manifold mod the general linear group, and you can put a quotient topology on it. And the upside of this is that you can classify vector bundles with the Grassmannian. I'm sure many of you have heard of this. So if you take the set of continuous maps up to homotopy from a topological space X to the Grassmannian in R infinity, continuous maps up to homotopy, being sloppy with base points, but then this is the same as the set of vector bundles over X, for example. So that's maybe one instructive example. We will not talk much about GLN of the real numbers in this course, but I thought this would be an instructive example. An example that is closer to what we'll be talking about here is the moduli space of algebraic curves. And that actually has the word moduli space in its name. Right, curves. And I'm going to add of genus G. And that is denoted M of G. And we'll probably hear more about it. You can add some like conditions of having so and so many boundary components, etc., or punctures. And this moduli space has a similar property. The property is that if I take the maps up to homotopy from X to G, then this classifies surface bundles.
Are those algebraic curves over R or C, or what is the field?
So when I say algebraic curve, then it's an algebraic curve over the complex number, but these are actually surfaces if you think about it as a real manifold. Does that answer your question?
Yes, thank you.
Thank you. So as I said already, the classifying spaces or the moduli spaces we are looking at in this masterclass are going to be classifying spaces of groups. And I hope you have heard about this. Otherwise, I recommend looking into the review package that Jennifer Wilson has put together, and I sent around, and it's on the website as well. This is, of course, a quotient of a contractible space and a group. So we usually have a group. Group acts on a contractible space, but that's not the only property, contractible space, that we need to have the classifying space of a group. We also need that it acts, if it's a discrete group, properly discontinuous and freely. And in a lot of the examples that we're looking at, we're going to also look at quotients where we have finite stabilizers. And that's then not the classifying space, but it will be fairly close to the classifying space. And in fact, so if X is contractible, let's call this BT, and G acts on X properly discontinuously, and has finite stabilizers. So every group element, only finitely many elements are fixed. No, sorry, the other way around. for every point in a space, there are only finitely many group elements that fix that point. That's stabilizers. Then the cohomology of the quotient of X, G with rational coefficients is going to be the same as the cohomology of the classifying space with rational coefficients. And that's something we're going to use a lot in the different examples. And I'm going to give you a few examples here. So, well, for example, Teichmüller space is let's say TG is a space of surfaces. I'm gonna have to be a bit faster, I think, to keep in time. We will have the mapping class space, the mapping class group act on the Teichmüller space. The Teichmüller space is contractible, and this acts properly discontinuously, but it has finite stabilizers. So the classifying space of the mapping class group is indeed the moduli space that we, but it's not the same as the Teichmüller space mod the mapping class group. So here you have to do something more, but rationally you could compute the cohomology with this. For the Grassmannian, we had that actually VK R infinity mod GK of R is the same as, or is, that was our definition of the Grassmannian in some sense. And this is classifying space of GLKR. So here we actually don't have any finite stabilizers, but as you can see, it's also finite dimensional. And maybe we'll see later that this space here is actually, infinite dimensional, and this space is finite dimensional. Another example that's is similar to the Teichmüller space is Color-Volkmann's outer space. Oh, I think you can see it. Is a chat question as well. Okay, that was a direct message. I'll look at that later. Outer space, Color-Volkmann's outer space, I will denote that by CV for Color-Volkmann, is the space of marked metric connected graphs with fundamental group the free group on n letters. That means you have, roughly speaking, n loops in your graph of volume 1. And so what is maybe the details of what that means are going to be talked about in a later lecture. But here as well, you have that now here you have that the outer automorphisms of the free group act on this. This is contractible, but there are finite stabilizers. So this is not the same as this. Number 4, we have our group G is going to be, we always start with the space. The space is, I'm going to call sum n, which is a symmetric space. It's the space of all space of positive definite quadratic forms on Rn. And here you have that, let's say, SLNZ acts on this, but again, you have finite stabilizers. As you will see later, we will still need and use these quotients. These are going to be interesting to us. And as the last example, for the symplectic group instead of the special linear group, there is the Siegel upper half plane, or half space, I guess, if G is bigger than 1. And here you have the symplectic group act on this, and that will give you an equivalent picture for the symplectic group. I have another chat. It's private again. Yeah, you're in charge of telling me when there's, you'll tell me when there's a chat question. Okay, great. Difficulties of hybrid. We knew that's going to come. So, the main point is of moduli space is that we are interested in the cohomology of these spaces. For multiple reasons, as in characteristic classes, etc., and that these what does it say? What does it say? Is it possible to have a homotopy / non-homotopy equivalent flipped in one? I thought the mapping class group X on the Teichmüller space was finite. Did I flip it accidentally? No, so what I wrote is that if, there are finite stabilizers of the mapping class group on the type. Thanks. So here, the questions is still here. The mapping class group acts on a Teichmüller space with finite stabilizers. So the quotient is not the same as the homotopy quotient, which would be then giving you the classifying space. So that's, I hope that answers your question. I hope I didn't misunderstand the question. So we're interested in the cohomology, either of the quotient or of the groups of the classifying space. And we already have some information about the cohomology. And so I want to start with cohomological stability. And so for these groups that I considered here, we have cohomological stability, and that means that I'm gonna write hi of Gn, and this is even true for integer coefficients. So for what? For the groups Gn, either SLNZ or SP2MZ, or mapping class group with genus N, or automorphisms of Fn. These groups are independent of N for N large in comparison to I. I'll write that as n is large in comparison to I, like this. Or in other words, yeah, this is isomorphic to Gn plus 1. And usually you have an inclusion from Gn to Gn plus 1, so you can get a restriction map in cohomology, and that will induce this isomorphism. And so these are, let's try to get the order right. Dwyer, Charney, Hara, Hatcher, Bookman, and many people more have worked on this. And for some, I'm not entirely sure whether they've really been the first one or not, but I believe this is true. And even more is true. You don't just know that they're equal. You even in these cases, you even know what this group is. Maybe not with integer coefficients. I mean, that might be a bit more complicated, but let's say with rational coefficients. So let's see, the cohomology ring of mapping class group in the rational range, in the stable range with rational coefficients is a polynomial ring with generators in even degrees. Is this Matz and Weiss? The cohomology ring of the outer automorphisms in the stable range is just Q, so it's just generated that the cohomology is basically trivial. This was proven by Søren Galatius. I don't think he will talk about that. He will talk about the high cohomology in the end, but want to say that here. For the special linear groups, we have a more complicated patterns of this polynomial ring. So you go on by adding 4 always. And for the symplectic group, you also go on by adding 4. So these are all polynomial rings. And these 2 results are by Borel. So that means for low dimensional, dimensions referring to the dimension of the cohomology, we already know a lot. Okay, I have to go on to high cohomology because that's really what I want to talk about. There is another question. Thank you. And the question is if the group is the mapping class group, what is the inclusion? You're right, there's no inclusion. If there's no, then actually this problem becomes a bit more difficult. One way to do this, wait, we don't know this actually for integer coefficients, right?
Yeah. You should have to go through surfaces with boundaries.
Oh, I see. You compare it to surfaces with boundary, and then with the boundary, if you have a boundary, you can have an inclusion by not doing anything on the new bit that you add onto the boundary. But you're right, there's no map like that. Thank you for the addition. All right, great. So I'm the organizer, but I forgot. I think I have an hour, right? Can somebody check the schedule? I think everybody has an hour, right? Okay. I was for a second worried that I only have 45 minutes, and then I was like really under time pressure. All right, that's good. We just started cohomology. Yes. So now, as I said here we understand what the cohomology is for n large in comparison to I. But what about either the other end or just everything else? And so I want to concentrate or focus on the other end right now. So what is this with? I'm being agnostic about. Good. Many questions. That means people pay attention. It is actually known that there's, and people know a lot of things. Induces. Yes, sorry, Natalie. I should have repeated exactly verbatim what Natalie said because you can't hear that through the microphone. But that's exactly what Natalie said in the comment. So the comment says there is what? There's no map.
You need to do a zigzag, right?
Natalie says that you need to do a zigzag.
Because you can close the surface.
You can close the surface.
They're asking if there's no such thing.
It's actually no.
The question is there a map of groups?
Oh, that's a great question. Sorry, I didn't see the question mark. And I thought it was a statement. That's a great question. There are experts in the audience right now that are thinking about it. We'll maybe go back to this after the lecture. I will leave on Zoom, and then people can chat about this. Yeah. Okay. Thanks. All right. I'm going to go on to high-dimensional cohomology, if you don't mind. And so the question here is. What happens if I is large in comparison to n? So the opposite. And it is actually, so for this, I'll first give a definition, and the definition is the virtual chromological dimension or VCD of a group is the cohomological dimension of a torsion-free finite index subgroup. Subgroup, if it exists. Subgroup. I also expel my, wait, I also expel, show my spelling here. Subgroup. And what's the cohomological dimension? The cohomological dimension is the largest I such that HI of the subgroup H with coefficients in any module, H module is non-zero or some. And it turns out that this condition is, or this number is independent of which finite index torsion-free subgroup you choose. And what does this mean? This means, in particular, this implies that, and in particular, it means that in all of our cases, this is actually very related to the fact that the cohomology of I ith cohomology of G with rational coefficients is 0 for I larger than the virtual cohomological dimension of G. So with integer coefficients, this is not true anymore. So there you will have some torsion elements.
So what do we need to assume about the group that this makes sense? I mean, we need a torsion-free finite index subgroup, and maybe it doesn't exist.
Yeah, so we definitely need that, but we do have that in the 4 groups that we are thinking about here.
Sure, but like, can we have a class of groups, big class of groups, where we know it makes sense?
So there is a bit more detail about this in the review package that Jennifer Wilson put together. I don't want to go into too much detail about that here because it's not relevant to the groups that we're discussing. Is that okay?
Yeah.
But we can discuss this later and look at the review package together, and maybe actually I will probably learn just as much from it as you would. Okay, so this already means that so let me say in about our groups, they all have finite virtual cohomological dimension, and those are 4G minus 5 for the genus G mapping class group. And it's a bit different if you have boundary components. You have 2n minus 2 for the outer automorphisms of Fn. And here it's similar that you can sort of have boundary components, and you get automorphisms and some other subgroups. No, not subgroups, other groups, and then this changes as well. And that was both of these things were also included in these results. You have it for the special linear group, and here maybe you could change the ring, and then you will get a different number here. Both of these results are again by one group of authors. For the symplectic group, you have this number. So all of these in particular do have finite virtual cohomological dimension. So which answers this question: if I is large in comparison to n, these are just 0. That raises then maybe the next question: what happens? Maybe we don't want to mean by high dimensional. We don't want to mean everything where it's 0. Maybe we just want to mean what happens in the top degree where it could possibly not be 0, or where we know that it's not 0, at least if you take some kind of coefficient system. So that we will adjust our question a little bit here. The answer, or an answer for this, is a duality principle that is in some sense similar to Poincare duality, but I will just say what it says explicitly. So for G equals to these groups that we've been talking about, we have the following property. So if you take cohomology close to the BCD of these groups, so let's say we just subtract a number I from that. And I mean, of course, you can also go all the way down to I equals VCD, so it doesn't have to be close to it, but the idea is we want to maybe figure something out about the large cohomology. This is isomorphic to the low homology of the group with a specific module D, or so D is a QG module and is called the duality module of G. And these results are, I think, no, not quite, but some of them are by the same people. So Hara also proved that, but then for the other automorphisms, this was proved by Svina Fein. And this result was this one for SLN and for the symplectic group. This was actually the earliest result of this kind by Borel and Sayre. Yes. That can be true. I thought I looked it up, and I just have my notes here. I don't know this by heart. Benjamin says that it might actually be 3 instead of 2. That could be true. I don't know off the top of my head right now. I don't have my notes.
Should be 2n minus 3.
Did somebody say something?
Kai-Uwe said something.
Okay, I can't hear you very well.
Oh, sorry.
Can you speak up a little bit?
I don't know. Maybe my mic is broken, but it should be 2n minus 3.
Okay, great. So we have 2 confirmations for 2n minus 3, and I'm definitely fallible, and I'll be happy to correct myself. All right. So the question now might arise: what is this duality? What is this duality module? And the duality module, you can actually describe this just by saying, or like, this is always the same as the cohomology in the VCD of the group G with the regular representation as coefficients. But that's often not very helpful to necessarily compute that. And in particular, we don't really know, for example, what it is for out FM. But let me tell you something about for SLN. So for SLNZ, Ralph Sayre proved that D is Q tensor, so the rationalization of the Steinberg module. And what's the Steinberg module? Well, the Steinberg module for any field is defined as the top cohomology. I'm doing this a bit backwards from what I normally do in talks. Well, this is a different TN now, but than we had earlier, of the Patzt building. And the Patzt building is a simplicial complex of flags. That means the simplices are with a P simplex is a a chain of subvector spaces of k to the n, in particular p plus 1 many of these that are chained like this. And this gives you a simplicial complex. And this simplicial complex is actually homotopy equivalent to a wedge of n-2 spheres due to Solomon-Titz. And that means the only reduced homology of this is indeed here. And since this simplicial complex is also n-2 dimensional, we automatically get that this is a free appearing group as being the top homology in the top dimension. So now we know another definition that maybe we don't know much about either, but in their proof of showing that this is n-2 spherical, this building, they also showed, gave a generating set and even a basis actually for this free appearing group. And it turns out that a basis for this are apartments. Given a basis of Kn, let's say V1 through Vn, an apartment or the apartment corresponding to this apartment is now you take the chains of subspaces, all chains of subspaces spanned by subsets, a subset of the spaces. Of the spaces. So, for example, if I have V1, V2, V3 is a basis of K to the K3, then what subspaces do I have? I have the subspace spanned by V1, by V2, by V3, and then I have the subspaces spanned by V1 and V2, the subspace spanned by V1 and V3, and the subspace spanned by V2 and V3. And then a chain is an inclusion. And so you have inclusions like this, and it's not hard to see that the result you get is always a biocentrically subdivided boundary of a simplex, or in particular, it's always homeomorphic to a sphere, and so it will give you, this sphere will give you a class in the Steinberg module, and so apartments generate the Steinberg module. Okay, so this is also true for, there's also a version for the symplectic group, for SP2NZ, there is a symplectic version.
Sorry for that.
Yes.
Consider they generate, you mean that they generate or even that they are bases?
So they generate another basis. They have some relations that Jennifer Wilson might talk about. There is a basis which you can choose by taking now basis is being used twice. The basis of this free being group, you can find generators of a basis of apartments by only using those bases of Kn that come from an upper triangular unipotent matrix. So upper triangular and ones on the diagonal, then that will give you a basis for apartments. All right. For the mapping class group, Hara found that there is a similar story using, instead of the Tietz building, you use, so T is comes from, let's say, an arc, also from a complex, a finite dimensional complex, also comes from a finite dimensional simplicial complex. But for out of n, odd of n, and out of n, we actually don't know of a finite dimensional complex that whose homology will give us this. We don't know.
So Peter, there are two parts in these theorems. One is whether there is such a duality, and the other is whether we can identify the module, right?
Yes, Natalie points out that there's two parts in this theorem. One is whether there is this kind of duality with some group that we can define this way, but maybe we don't know much about. And the next part, another part of this theorem, in particular of this theorem of Hara and Borel-Sayre, was that they identified these duality modules in terms.
How do they prove? How are these theorems proved? Is it
so you have to find, I mean, I think Michaela Janssen will go into it. So you don't need to know what this is to find the duality. The big difference that
you can just show the duality.
Yes.
No, you can't. Like,
Oh.
when I prove duality, we're going to use the sign that prove the duality. Yeah, to prove the duality. But then is there a consequence then that it is the duality module unique? It's unique. It's always unique.
It's always this. So the big difference is that we will Michaela will have to find a contractible space that she needs to borderify, and that's her talk next. And the big difference here is going to be that for every of these groups except for the outer automorphisms, those spaces are manifolds, and then you can use Poincare duality to understand something about this. But for automorphisms, the space is going to be the outer space, and it's not a manifold, and so there you can't use Poincare duality. Okay. Good. So, chat. Oh my God. That's good. That's good. Oh, I'm sorry. The question that Natalie posed was, how can we possibly not know what the duality module is and still prove the theorem? And the answer was, we don't need to know what it is in terms of a simplicial complex like that. And the difference there is we get it out just because there is a some of these spaces that we use for that have a what's the word I'm looking for? Manifold structure, and some don't. All right, good. I want to say two more things very fast. And so one thing is there is a conjecture by Church, Farb, and Putman that has led many, including me, to think about these problems more lately. And this conjecture is in particular for the sequence of the mapping class groups and the special linear groups, and the conjecture says that the high dimensional cohomology, so when I, in this case, if I is, or n is big in comparison to I in this way, so low codimension in some sense, that, which is by Borel-Serre duality the same as this, that this is 0 for n large in comparison to I. So maybe it is due time that I'll make a picture, a small drawing to show you what we know. So if this, I think I will answer the question after. Oh, I'm sorry. Church, Farb, and Putman. There is a question in the chat, though. I see that now. I will come to your question in a second. So if this symbolizes all of hi of Gn, then we know that in a range like this, roughly, we have stability, chromological stability. In a range like this, roughly, we know that it's 0. And now the conjecture says that in a parallel range to the virtual chromological dimension, you're also 0, or in maybe more generally, you have some kind of, let's say, conjectural stability. Maybe I want to say that in particular, I want to say that because I shortly want to tell you what is the progress on this conjecture so far. So the progress so far is that in the virtual...
Quick question. Why have you drawn the virtual cohomological dimension curved? Isn't it?
Because it's a curve. I mean, okay. So you're right.
Oh, I thought you were talking about the mapping class group. Okay.
No, you're right. I think
you erased it from the conjecture, didn't you? Wasn't the mapping class group in the conjecture?
So the mapping class group is in the conjecture, and it is in their conjecture. That conjecture is wrong, as we will see in the progress in a second. But yes, you're absolutely right. I have thought personally much more about the linear groups, and these are parabolic, quadratic virtual cohomological dimension. But you're absolutely right. We will think a lot about these mapping class groups here, and they're actually linear. So maybe it's worth also considering a similar graph where they are linear. Thank you, Jens. So the progress has been that for SL and Z, in the virtual cohomological dimension, this is 0 for n at least 2. This is by Lee and Charber in the 70s. And then in codimension 1, this is also 0 for n greater equal 3. This is more recent progress by Church and Putman. We also know that that in the virtual chromological dimension, sorry, in VCD, the mapping class group is 0. This is a result by Church, Farb, and Putman, but in codimension 1, this is not 0 when G is at least 7, and this is a result by Chan, Galatius, and Payne, which Søren Galatius will talk about in the mornings of the next days. So in summary, and then I will open up for questions, the goals of the masterclass will be to understand how to prove groups are duality groups and compute their dualizing modules. So two parts, as Nathalie points out, how to understand, how to use the description of the dualizing module to compute cohomology groups. So how can we use a description of the Steinberg module, for example, to see that these things are 0, how to or understand why the conjecture is wrong for the mapping class group, and we will also understand some of the subgroups of these groups of that we've been considering in form of congruent subgroups or Torelli subgroups. So, well, thank you for paying attention. Okay, that was just a thanks. Good thing I didn't. So, are there any questions for now?
The duality theorem, it works for large I or?
So it's been asked whether the duality theorem works only for large I. No, this is not. This theorem is true for all I. If I is too large, in fact, then this number will get negative, and it will. So there's not really. So it means in particular that this will be 0, but vice versa. If as we've seen, there's no cohomology higher than the virtual chromological dimension. So for example, if I is negative, then it's even also true. The statement is also true. So it's for all I. There was a question in the chat that was already answered by Jens. Great. Helping me out here. A basic question: if AH is a subgroup of finite index, is BH homotopy equivalent to BG? No, that's not true. It's also not true that they have the same chromology or anything, not even rationally. So, for example, for SLNZ, we see that in the virtual. Yes, there is for the people here. This chat is in the way. For the SLNZ in the virtual chromological dimension, the cohomology is 0. But for congruent subgroups, for some congruent subgroups, this is actually not 0 and growing. So I hope that answers your question with an example as well.
Well, just one addition. The classifying space BG is a complete topological invariant for the group. You can recover the group. You just take the fundamental group.
Yes.
So
yes. Great point.
Groups never have homotopy equivalent classifying spaces.
Absolutely true. Great point. So like you can recover the group by the fundamental group. I wanted to say a little bit more because you actually, what you do have is that This theorem, if you have, is true actually for every finite index subgroup of these group automatically. That is with the same dualizing model. So you can actually, if you have congruent subgroups of SL and Z, then you can plug in these congruent subgroups here and the Steinberg module that we used for SL and Z, and you still have this duality statement. So that is the closest that you can get that they are related, but they're definitely there's not even that they are zero as well. Wait, Jens, Andrea is asking a question and you can hear it. I will repeat it for you online, and then you can ask your question, Jens. Yeah, Andrea, please. Sorry.
So you just say that if G is a finite index subgroup of, let's say, sub n, then the duality model for G is still H, the cohomological dimension of what with coefficients.
Yes. So Andrea just asked in disbelief the exact same thing that I just said, and I'll just repeat it again to reiterate. If you have SL and Z, or if you have a finite index subgroup, the finite index subgroup has the same virtual cohomological dimension, and you have also that it is a duality group with the same duality module as you had before.
So this implies in particular that H is D of G with coefficient Q of G doesn't change if you pass to a finite index subgroup. Because the formula that the last formula that you give, it already depends on the group.
I mean,
the universal
so here you will have the subgroup as well, though, right? Yes.
In the dualizing
model, you give a formula that should work for every group.
For every finite index subgroup of SL and Z.
Yes. And whether you, but how should I interpret G and QG? Which G and which?
No. This it doesn't matter. Like, this is going to be isomorphic to. So if you take H to be a finite index subgroup of G, then this is actually going to be isomorphic. This is going to be the same number, and this is going to be isomorphic. Yeah.
So maybe
Jens.
May I interject something?
Sure.
So there is a geometric description of that module as the cohomology with compact support of a free CW complex that the group acts on.
Yes.
And that CW complex can be chosen to be the same for G and H. Yes. Because if you act freely by self-permuting homeomorphisms on a CW complex, any finite index subgroup will do the same.
Yes.
Right. So
this is
you get that from VCD.
Yeah.
You get that from a geometric description of that module.
So if you recall from the beginning that we always had groups acting on certain spaces, then you can use, we will use these spaces, in particular the Teichmüller space, the outer space, and the symmetric space, and show that, and can use this action to define these dualizing modules. That's absolutely correct. Thank you for that. And then you can, H just acts on this space as well. Okay, great. Lots of questions.
What I wanted to say, just a short comment clarifying this matter with finite index subgroup. Is this geometric idea that if you go to classifying spaces, you have a finite sheeted covering. And then one thing you have additionally, but that you don't have otherwise, is the transfer map. I think you haven't mentioned that yet. And I think that helps to clarify the matter and to understand what's going on.
Good.
So as in any finite sheeted covering, you have the transfer map going in the wrong direction, so to say.
That's true. We are actually, yeah, we're not using that much in this area, but yeah, that's a good point. You have that. With the transfer map, you can go back and forth between, or like you can compute the cohomology of one or the other using going through the co-invariance. Yeah, thanks of the quotient. All right, let's stop the recording, and I will